Welcome back to AI Paper Slop. We are getting straight into it today with a massive new release from the BAAI Orca team called uh, Orca, The World is in Your Mind.
It's a big one.
Yeah, and for you out there building foundation models or working in embodied AI, here's the core insight you need right up front. The field is basically hitting a hard ceiling with specialized next token, next frame, and next action prediction models.
Right, they're plateauing.
Exactly. So Orca proposes a fundamental shift away from all of those, moving instead to next state prediction. They built a model that learns a unified world latent space from multimodal signals using like 125,000 hours of raw video.
And 160 million event annotations.
Yep. And to pull this off, they split pre-training into two paradigms. You've got unconscious learning for raw, continuous physics and conscious learning for sparse, language-annotated events. And this dual approach creates a totally frozen encoder backbone.
Which is wild when you think about it.
It really is. That frozen state is then read out by lightweight decoders for text, images, and action. And the major takeaway for you developers watching this series, scaling up this pre-training reliably decreases loss. It outperforms similar-sized models like Qwen 3.5, and remarkably, it improves robotic action generation without ever seeing a single action label during pre-training.
Zero action labels.
None. So let's get into the architecture and, why this shift to state prediction is so necessary right now.
Well, it is arguably the most necessary pivot the field could make. The BAAI team is essentially calling out the siloed approach we've been stuck in for years.
Right.
I mean, if the goal is artificial general intelligence or even just like a physically robust AI, optimizing for isolated downstream modalities is just a dead end.
Yeah, we've basically been treating the symptoms of intelligence rather than the root cause. Like, we have next token models, your DeepSeeks or Qwen's handling semantic understanding.
They know the word apple is usually followed by the word false.
Exactly. And then we have next frame models like Sora handling visual dynamics. But, we all know Sora can completely hallucinate physics.
Oh, yeah. Objects just phasing through each other.
Right. Fluid dynamics acting like solid blocks because it's only optimizing for the next plausible arrangement of pixels, not the actual underlying physical truth.
Yeah, it's just aesthetics, really.
And finally, we have next action models handling robotic affordances, which are completely bottlenecked by data scarcity. So Orca's goal is to bypass all these silos, right? To create a self-emerging intelligence system that internalizes physical laws and causality into one single latent space.
And to understand how they actually accomplish that, we have to look at how they formalize the world state conceptually.
Okay, lay the math out for us.
So they define a mapping from multimodal world signals, which they call X, so everything from text prompts to continuous video frames, into a compressed latent world state, which is S.
Got it. X goes to X.
Right. And the mathematical objective is no longer guessing the next word or, the color of the next pixel. The objective is to predict the future state, like S at time t plus delta.
Over a specific time horizon.
Exactly. And making that prediction relies on two crucial variables. You have the implicit physical dynamics, which they denote as ZEET, and the explicit semantic conditions, which is SEET-TET.
Okay, let's translate those variables into practical terms for everyone. The explicit conditions, the context, those are pretty straightforward, right?
Yeah, those are just human instructions, task prompts, text constraints.
But the implicit dynamics, the ZEET, those are the unobserved factors driving state changes. We are talking about like gravity, object mass,
Right.
Environmental forces.
Yeah. So the model is forced to predict the future state based on the current state, the underlying unobservable physics, and the explicit human intent.
And because that time horizon can be stepped forward or backward, it theoretically models both forward prediction and backward causal backtracking.
Which is a massive departure from standard autoregressive models. Huge. When you force a model into a latent state bottleneck that has to account for those implicit physical dynamics, you are forcing it to learn the actual mechanics of the scene.
Think of the distinction kind of like baking. Next token prediction is like memorizing a recipe.
You know the words, but not the taste.
Exactly. You don't know what flour tastes like. Next frame prediction is like painting a picture of a cake. You know what a rising cake looks like, so you can generate a nice video of it. But next frame prediction is actually understanding the chemical reaction of baking.
I like that analogy.
You aren't just guessing the next pixel of the oven camera, you're tracking the latent variables of temperature and doneness over time.
Because if you only predict pixels, you might generate a highly realistic video, but the model doesn't inherently understand the heat transfer. It just knows pixel cluster A expands into pixel cluster B.
Right. Next state prediction forces it to internalize the concept of heat itself.
As a latent factor, yeah.
Yeah. But I have to challenge the core premise here, though. How do you actually train a transformer to learn a chemical reaction or a physical law without explicitly programming a physics engine into it?
Wow.
Like, you can't just dump raw video pixels into a transformer, apply a loss function, and be like, hey, figure out gravity. The pixel space is way too noisy for that.
Yeah. The curse of dimensionality guarantees it would just memorize local textures.
Exactly. Instead of global physics.
That is exactly the pitfall the Orca team avoids. And they solve it through that dual learning paradigm we mentioned.
The unconscious and conscious learning.
Right. So the unconscious learning phase is purely self-supervised. It's designed to capture natural, dense state transitions from continuous video.
Like wind blowing leaves or water flowing.
Exactly. The model is trained to predict the latent representation of the next frames, not the raw pixels. By operating entirely within the latent space, it avoids all that high-frequency pixel noise you mentioned.
So it isn't trying to reconstruct the exact lighting glare on a leaf?
No, it's predicting the evolution of the spatial state. It learns that objects move downward at a consistent acceleration.
So it internalizes natural evolution, the implicit physics. But, I mean, just watching leaves blow in the wind doesn't give you causal reasoning.
No, it doesn't.
A model could perfectly simulate a falling apple, but never understand why it matters to a human task or what caused it to fall.
Right, and that is where the conscious learning paradigm comes in. This second phase captures sparse, meaningful state transitions using textual constraints and visual question-answering supervision.
Okay, so if unconscious learning is learning how the physics of a melting ice cream cone looks over time.
Conscious learning learns the semantic concept that the ice cream melted because it was exposed to heat.
Ah, so it operates at the event level, providing causal explanations.
Exactly, and task intention.
And the scale of data they use to align these two is just staggering. For you guys managing data sets, they used 125,000 hours of continuous video for the unconscious physics engine.
And 160 million event annotations for the conscious semantic engine.
Right, covering egocentric interactions, exocentric manipulation, action-free robot executions. But for the ML engineers watching, this raises a massive infrastructure question.
Oh, for sure. Bandwidth.
Yes. We all know language is incredibly low bandwidth compared to 125,000 hours of high-res video. If you feed both into a single model, how do they prevent the language side from severely bottlenecking the rich visual data?
The solution is their strict encoder-decoder separation. The encoder acts as a massive funnel. It absorbs both the dense visual signals and the sparse language signals, mapping everything into that unified latent world state.
So they aren't competing for bandwidth.
Exactly. The conscious and unconscious objectives act as complementary constraints on the exact same latent space. The visual data forces the representation to obey physics, while the language data forces it to group those physical changes into human understandable events.
And once that highly constrained latent space is learned, the Orca team does something incredibly bold.
They freeze it.
They completely freeze the encoder. They lock in the world model.
Total parameter freeze for the backbone.
See, I have to push back on this architectural choice. If they completely freeze the backbone after pre-training, aren't they just hard capping its intelligence?
How do you mean?
Well, we know from fine-tuning large language models that freezing the base model can severely bottleneck its ability to adapt to complex, out-of-distribution edge cases later.
That's generally true, yeah.
So if a robot using this model encounters a totally novel physical environment, a frozen encoder can't update its internal physics engine. How is a frozen architecture not a massive liability for future scaling?
It sounds like a liability until you look at what they're actually trying to prove with this paper. The authors state explicitly that they aren't chasing task-specific state-of-the-art performance by fully fine-tuning a monolithic model.
Oh, so the freeze is intentional for the experiment.
Yes. They froze the backbone specifically as a probe to validate the latent space itself. The hypothesis is, if the world latent space is truly robust and unified, then a frozen backbone should be able to support highly performant readouts across entirely different modalities just by training lightweight, throwaway decoders.
Wow, okay. So it proves the intelligence lives in the state representation, not in downstream task memorization.
Exactly.
It's like they've built a universal engine block, that's the frozen encoder, and the researchers are just swapping out the transmission depending on whether they want to output text, images, or robotic movements.
That's a great way to put it. The encoder just outputs the current world state, And the modality-specific decoders translate that state into the format you need.
And looking at the engineering of those decoders, particularly the vision readout, it is a masterclass in parameter efficiency.
Oh, the way they use stable diffusion.
Yeah, they didn't even train an image decoder from scratch. They mapped Orca's predicted visual latent state into image space using a pre-trained stable diffusion 3.5 decoder.
And even there, they maintain extreme discipline with the parameter freezing.
Right, they completely freeze the variational autoencoder, the VAE, handling pixel compression, and they freeze the multimodal diffusion transformer weights of SD 3.5.
So they preserve the inherent generation capabilities of the diffusion model without destroying its weights.
The only things they actually train are a multi-layer perceptron adapter and MLP and low-rank adapters, or LoRa's, attached to the decoder's attention projections.
It's so smart. The learned latent state from Orca passes through the MLP adapter into one path of the diffusion model, steering the attention mechanism, while the target image is denoised in the other path.
It's a highly efficient way to translate an abstract world state into a high-fidelity image without retraining a multi-billion parameter diffusion model.
Incredibly elegant. But you cannot process 125,000 hours of video without hitting a brutal compute wall.
Oh, absolutely not. The infrastructure section of this paper is essential reading for anyone managing GPU clusters. They trained this on H100s, and they noted severe communication stalls when using standard FSDP2 fully sharded data parallelism.
Yeah, anyone doing distributed training at scale knows this pain point. When you shard massive model parameters across thousands of GPUs, the all-gather operations can completely choke your network throughput.
Because if the parameter aggregation from the network isn't perfectly overlapped with the actual matrix multiplication happening on the chip...
But GPUs just sit there idle, waiting for weights to arrive over the network.
And when you are renting H100 clusters, idle compute time is basically setting money on fire.
Literally.
So to fix this, the Orca team bypassed the standard FSDP2 scheduler and implemented a custom forward and backward prefetching system.
They mathematically overlapped the parameter all-gather network requests for upcoming layers with the computation happening in the current layer.
Aggressively hiding the communication latency behind the compute time.
Right. And they combine that prefetching with activation recomputation and a chunked cross-entropy loss.
Because processing long video sequences causes crazy memory spikes, right?
Exactly. You easily get out-of-memory errors during the loss calculation.
Yeah.
But by breaking that massive loss calculation into smaller sequential chunks, they kept the memory footprint totally stable.
And the final throughput numbers really reflect how critical these optimizations are. They hit 2.91 samples per second per GPU on those H100s.
Which is huge.
Yeah, that is a 3x improvement over the FSDP2 baseline and a 4.4x improvement over the standard star VLA pipeline. When you're training a 4 billion parameter model on thousands of hours of video, a 3x throughput multiplier is the difference between a project taking 1 month versus taking an entire financial quarter.
Right. It makes or breaks the research budget. So they have the infrastructure optimized, the data pipeline built, the backbone frozen. The next logical step is evaluating whether this mathematically dense approach actually translates to better benchmark performance.
Which brings us to the scaling laws. They looked at scaling behavior across two model sizes, a 0.8 billion and a 4 billion parameter model, scaling the pre-training data all the way up to 8,000 hours of video.
And the total loss curves for both models show a smooth, continuous downward trend.
The next state prediction paradigm doesn't easily plateau. It scales predictably, which is exactly what you need before committing tens of millions of dollars to a compute run.
And that stronger latent pre-training directly translates to better downstream readouts. They benchmark the Orca 4B model against specialized, fully fine-tuned vision language models of similar sizes, like Qwen 3.54b and Gemma.
And remember, you guys, Orca's backbone is frozen. It hasn't been explicitly tuned on the benchmark-specific training sets.
Which is a massive handicap.
Despite that handicap, Orca 4B significantly outperforms Qwen 3.5 in cross-benchmark capabilities. Like, look at the state transition evaluations, which measure how well a model predicts future states. Orca 4B hits 64.13%.
While Qwen 3.5 was at, what, 51.86%?
Yeah, 51.86%. That is a massive 12% absolute improvement just from having a physically grounded world model.
It also beat Qwen in common sense reasoning and dynamic motion. And it showed incredibly strong results on 3DSR bench, testing spatial relations.
Because if a model understands that physical state A evolves into physical state B, it inherently understands the 3D space those objects are moving through.
Without needing explicit 3D mapping data, yeah.
The conscious learning phase forced it to align those visual physical changes with causal text. But honestly, the text and image generation results are just the warm-up for the biggest revelation in this entire paper.
Oh, the action generation readouts.
Yes, this section completely upends the current consensus on how to build embodied AI.
It really does.
To set the context for anyone who might not work in robotics, the biggest bottleneck in the field right now is data scarcity. Getting high-quality teleoperation data where a human manually pilots a robotic arm is painfully expensive and slow.
You can't just scrape a trillion tokens of robot joint angles from the internet like you can with text.
Exactly. As a result, robotic policies usually fail to generalize. They overfit to exact lighting conditions or the exact cup shapes from their tiny training sets.
And the industry consensus has basically been, well, we just need more teleoperation data.
But here is the breakthrough in the Orca paper. As they scaled up the raw video pre-training data, the action readout performance improved dramatically. And crucially, absolutely no data with action labels or motor commands was used during that pre-training phase.
Zero teleoperation data, zero joint angles.
None. The pre-training was entirely passive video and event annotations. Yet the model developed an emergent capability for embodied action generation, purely from understanding how the physical world dynamically evolves.
This cannot be overstated. They achieved zero-shot policy improvements for downstream robotics just by having the model watch video of the world.
Because the model learned the implicit physical laws, the next state prediction, it inherently learned the affordances of objects.
It knows how an arm should move to pick up a cup, because it understands mass, friction, and how a cup state changes in 3D space when acted upon by a force.
It completely reframes robotic action. Instead of treating action as this unique, isolated modality, it treats action as just another manifestation of a state transition.
Right. If the model knows the current state of the room, and you give it a prompt requesting a desired future state,
the frozen latent space can map that difference and output the exact motor commands needed via a tiny, lightweight decoder.
instead of painstakingly collecting thousands of hours of tele-up data for every specific robotic arm, you can bootstrap a massive world model with raw, passive YouTube videos.
Freeze it, and just train a tiny action decoder on a sliver of robot-specific data. The generalization and physical grounding come from the video, not the tele-up data.
It completely validates their central hypothesis. Next state prediction isn't just a different mathematical loss function, it's a more fundamental representation of reality.
By forcing the model to calculate the implicit dynamics, it actually learns how the world works, rather than just memorizing surface-level correlations.
So to synthesize this for everyone building foundation models out there, Orca proves that next state prediction creates a highly robust, unified latent space.
Yeah, by splitting the learning into unconscious physical data and conscious causal data, you build a world model capable of powering diverse, modality-specific decoders.
And with their aggressive infrastructure optimizations like the prefetching, this provides a highly scalable blueprint for the next generation of AI systems.
It's a blueprint that fundamentally moves the industry away from passive, task-driven memorization engines toward active, physics-grounded world learners. And I want to leave you all with a final, really provocative thought straight from the conclusion of this paper.
Oh, about the boundaries of human cognition.
Yes, Orca's mathematical framework mapping multimodal signals into a latent state to predict future evolution isn't strictly limited to human senses like vision or language.
Right, the math doesn't care what the input is.
Exactly. If this state transition model works so efficiently for extracting hidden physics from standard video, what happens when we feed it multimodal signals from entirely beyond human perception?
Like macroscopic astronomical data.
Yes, or raw physical force sensor telemetry, or even microscopic quantum mechanics observations. Could a model predicting the next state of these invisible dynamics self-evolve to discover physical laws or causal relationships that human scientists haven't even theorized yet?
It's a wild thought.
The world is currently in its mind, but soon that mind might be analyzing a reality vastly larger than our own. Keep building, keep experimenting, and we'll catch you on the next deep dive into the research pushing the boundaries of AI right here on AI Paperslop.